Hi guys, today this is the fourth episode of the math series, and today we'll be looking at four of the most difficult problems that the 2025 Mathemania competition has to offer. Credits to them, credits to them, uh, credits to them, of course. I believe these are difficult because the solutions and the solution for these is pretty subtle. But who knows? There can be multiple solutions. Hey, and for these problems, if you have an alternate solution for these problems, please put them down in the comments. I really like to see a different perspective from my solution. Speaking of solutions, let me start by showing my solution for problem 1. If we decrease the second term of each multiplication by 1 in the expression, how will expression A will decrease total? Before you try and solve it, these terms here, yeah, they're all multiplications. They're multiplications, okay? No sums. No sums. The only part where there are sums is the sums of those multiplications. You need to multiply these first and then add them to get the value of A. And then the question is asking us to subtract A with the sums of the same multiplications, but with the second term subtracted with 1. Let's note down. Sorry. I was about to give you my solution, and I almost forgot. And I almost forgot that. And I almost forgot. That I should allow you to pause the video and try and find out the solution yourself. Got the solution? Well, you can compare it with mine. If your guess was 152, you're correct. Let's see. Well, let's find out why it is 152. So let's note down all the products in A. So we have 2 times 3, 3 times 4. Oh yeah, we mathematicians use dots as a simple way of saying we are multiplying these numbers. 2 times 3, 3 times 4, 4 times 5, 5 times 6, 6 times 7, 6 times 7, 7 times 8, 8 times 9, 9 times 10, 10 times 11, 11 times 12, 11 times 12, 12 times 13, 14, 13 times 14. Yeah, you get the point. We're at it. Yeah, you get the point. There will be multiplications all the way to 17 times 18. Okay, so let's find the value of the multiplications if we subtract the second term, as the question says. So 2 times 3 will become... Okay, so let's denote our new value of A as A2. 2 times 3 will then become 2 times 2, or 2 squared. 3 times 4 will then become 3 times 3, or 3 squared. 4 times 5 will then become 4 times 4, or 4 squared, and 4 2. And then that will continue until 17 times 17 or 17 squared. We're subtracting the second term, okay? So 3 becomes 2 as we subtract it with 1. The 5 here, the 5 here, the 5 here that becomes 4, and the 5 here becomes 4. And so on. And now it is asking us, how expression A will decrease the total? It's basically asking us, what is the value of A subtracted with A2? That would be 2 times 3 plus 3 times 4 plus all the way to 17 times 18 subtracted with this value. Or 2 squared plus 3 squared all the way to 17 squared. Well, you could manually calculate this, but that would take way too long. Plus, this is a math competition we're doing, so the time is very limited. So let's find out a clever way of subtracting them. We can write 2 times 3 as 2 times 2 plus 1. 3 times 4 as 3 times 3 plus 1. And so on. We can do this for all the multiplications till 70 times 18. (70 times 17 plus 1). These are of the form n times n plus 1, which is n squared plus n, because we expand this n because we're expanding the brackets for n, because we're expanding these brackets, because we just expanded these brackets. And now we're subtracting we're subtracting the square with this. These are of the form n squared. N squared. If we simplify this, let me tell you why these are important later. For now, we'll simplify it. Will become 2 times 3 minus 2 squared plus 3 times 4 minus the 3 squared, because this minus here is being distributed to all the terms inside this bracket, all the way to 17 squared, which is why we're subtracting. And note that this subtracted with this is the same as subtracting these individual terms together. And then we'll subtract this all the way to 17 times 18 minus 17 squared. And these are of the form n times n plus 1 subtracted with n squared. We know n times n plus 1 as n squared plus n. Oh look, the n squares cancel out, leaving n. Wait, we just simplified n times n plus 1 subtracted n squared, and we got n. And since n can be any integer, that means that we can simplify this long sum into just n, because n squared plus n minus n squared is just n. So therefore n times n plus 1 minus n squared is n. The same structure as before. The same structure of this subtraction. So what this means, we will be able to simplify this long sum into just a sum of the positive integers from 2 to 17. So that long sum just simplified to 2 plus 3 plus 4 plus 5 all the way to plus 17. How elegant is that? But now we have a final step, trying to calculate the sum. I remember from number theory. I remember from when I studied sequences that the sum of all natural numbers from 1 to n is just n times n plus 1 over 2. I'll make a visual proof on why this is true in another video. For now, we'll focus on trying to solve problem 1. This is just the sum of all natural numbers from 1 to 17 subtracted with 1. So we'll plug in 17 times 17 plus 1, or 18, or 18 divided by 2, and then we'll subtract by 1 to get the sum of this. We can cancel the 2 with the 18. 18 divided by 2 is 9. So we get 17 times 9 subtracted with 1. 17 times 9 is short, so I'll manually multiply. You can skip this part if you want. Wait. And we get 70 times 9 as 253. Subtract that by 1, and we get 252. So the difference of A with A2 is 252. Oh, wait. My bad. Okay, sorry, my bad. My addition skills was wrong. Okay, sorry. I'm very sorry. And sorry. 70 times 9 is 153. I'm very sorry. Okay, listen. Even math bros like me can make mistakes. Okay. That's just 153. So, sorry. 70 times 9 is actually 153, not 253. My bad. I did a miscalculation. And then we get this as 152. So the difference of so the actual difference of a minus a2 is 152, and that's the answer. Moving on to problem 2. What is the size in degrees between two hands of a clock at 1410? The two hands of the clock being the minute hand and the hour hand, okay? Pause the video if you want to solve this problem. I'll give you a hint to this. This is a trick question, and the answer isn't as obvious as it seems. And that's the only hint I'll give you. For when I've solved this the first time I solved this problem, I made a mistake. I made a mistake that I believe that other people like me will also find while trying to solve this problem. And I'll show that mistake to you so that you can avoid it. And if Madam Mania tries to include this question again, which is not very likely, which is not very likely. So a clock is like a circle, okay? Keep that in mind. And in a circle, a full rotation is 360 degrees. Let's look at how much degrees the hour hand, the shorter hand, goes if 1 hour passes. There are usually 12 hours on the clock, so that means that there's 12 sectors to this circle, to this imaginary clock. Note that my drawing is not drawn to scale, okay? There's obviously no 12 sectors, just trying to demonstrate. Just 12, then use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so 1410. That is written in the 24 hour system. If you convert that to the 12-hour system, we get 2:10 p.m. It's not a.m., okay? If it were a.m., it would have been like it would have like 0. It would have been like 0 to 10, not 14:10. Since there's 12 sectors, each sector will have 360 degrees divided by 12, or 30 degrees per one sector. So the amount of degrees the hour hand turns per hour is 30 degrees. But we also want how many degrees the hour hand turns per minute. Do you want to guess why? I'll tell you why later, when we find the amount of degrees the minute hand turns per minute. So since there's 60 minutes in an hour, we will just divide this 30 degrees with 60 minutes to get the amount of degrees turned per minute. 30 divided by 60 is just 1/2. You probably know how to divide. You probably know how to divide, so I'm not going to tell you how I got 1 divided by 2 from 30 over 60. Well, if you don't know what dividing is, maybe, to be honest, maybe this video isn't really suitable for you. As there's gonna be a lot of dividing in this one. Okay. And then now our hour hand is complete. Now let's look at how many degrees the minute hand turns in 1 minute. Since there is in each sector there is five of these. Sorry, my bad. In 1 hour there is 60 minutes. And since one for rotation is equal to 360 degrees and 60 minutes, those 60 minutes compose 1 hour, we can say that 60 minutes is equal to 1 full rotation of the minute hand. So to get the number of degrees turned per minute on the minute hand, we'll divide 360 degrees with 60, the number of minutes. 360 divided by 60 is 6 degrees. Minute hand, 6 degrees per minute. Okay, so 2:10 p.m. is this. Alright, normal people might think, this is where people make the mistake. Since normal people trying to find that they're trying to find how many degrees each minute, how many degrees the hour and minute hand turns is easy. But they forgot one thing. Here's how normal people would say. 10 minutes have passed, so they multiply this 10 with 6 to get a number of degrees turned in 10 minutes. So 6 times 10 for the minute hand, that is 60 minutes. 60 degrees. 60 degrees. And then for the hour hand, 30 degrees per hour, 2 hours have passed, so they multiply 2 with 30 to also get 60. But then they'll see there is no difference between the hour and the minute hand, between the degrees turned by the hour and minute hand in 2:10 p.m. Do you wonder why? Do you see the mistake? Uh, so the yeah, so they'll just so they're just so they're just say th- there is no difference. This problem is unsolvable, like they'll say. This is where they've made a mistake. That listen, the hour hand also moves, you know. Oh, the hour hand also moves, you know, and starting from 2 p.m. 10 minutes have passed since the hour to reach 2 p.m. to reach 2 p.m. So the hour hand is going to move a little bit, and that's the mistake. They didn't consider they didn't the number of people didn't consider that they considered that the hour hand also moves. It moves very slowly if you measure if you the degrees turn is the degrees turn is very low if measuring degrees per minute. If measuring degrees per minute. But yes, it moves. So since 10 so 10 minutes have passed. So it's going to move 10 minutes times this to get the number of degrees turned within 10 minutes by the hour hand. 1/2 times 10 is 5. So an extra so within 10 minutes the hour hand turned an extra 5 degrees. Turn an extra 5 degrees. So the number of degrees turned by the hour hand isn't 60. It's actually 65. And now we can finally find the difference between the minute between the degrees between the minute hand and the hour hand. 65 minus 60 is just 5 degrees. And that's our answer. I hope you didn't find them. I hope you didn't make the mistake that most people would do when encountering this problem. Well, to be honest, I did. Well, to be honest, I also stumbled on this mistake when I first solved this problem. But then I double checked again and finally found where my mistake was. So remember, people, double check your answers. You may find a hidden mistake that you haven't spotted. Problem 3. Well, this is new. This is a logic puzzle. I used to do a little bit of Sudoku a little bit, but I don't think it's going to really involve in the solution here. I traveled to an island inhabited by knights who always tell the truth and naves who always lie. Furthermore, the island's inhabitants only answer questions with yes or no. Here, I met Alice and Bob. I asked Alice, "Are you both knights?" After Alice gave me an answer, I figured out the type of each. What was the type of each? Pause the video if you want to figure this out. What makes this problem difficult is that we aren't even given given what Alice replied. But still, what makes this problem elegant is that we can still determine the types of Alice and Bob without even knowing what Alice said. Because the question gives the fact that I figured out the type of each. after Alice gave me an answer. Gave me an answer. That is an important clue. Keep that in mind. Since this is a statement in the question, we can say that statement must be true. So it cannot be E. Because if the answer were E, it would contradict with the fact that I know the type of each after Alice gave me the answer. So now we have E out of the way. Let's figure out the possibilities that Alice could say. The first possibility is that Alice was a knight and said yes. The second case was Alice was a knave. Alice was a knave. Naves lie. Naves lie. So instead of saying no to the question, are you both knights? She is going to say yes because naves lie, and since she's a knave, she's going to lie. She's going to lie. Then on the third case, Alice was a knight and said no. And then the final case is when Alice was a knave and said no. But wait. Let me sit down a little bit. Let me sit down a little bit. Let me sit a little bit. Well, off the bat, we can eliminate the fourth. We can limit the fourth case. Why? Because in the fourth case, Alice said no, and she was a not, and that she was a knave. So that means she would have said yes. That she actually said yes, but then she lied and said no, meaning that there are two knights. But there was only two people. So there's a contradiction between the number of knights and the number of people that are knights. So we can't consider the fourth. Well, how about when Alice was a knight and said yes? Then, if Alice was a knight and said yes to this question, then Bob will also be a knight too, in the first case. But what if Alice were a knave? But what if Alice was a knave? What if Alice was a knave, and she will also say yes. She will also say yes, but the yes is also the same for when so the response from the knight and the knave, the response from the knight and the knave are the same. So we can't. So if Alice, so if Alice were a knight and said yes, and said yes, we couldn't. And if she said yes, and if she was a knight, then we can't really determine. That we can't really determine it. That we can't really determine if Alice was a knight or a knave, because we're just assuming that Alice was a knight and said yes. Not the truth. It's only an assumption. So we don't. So if he says yes, then we don't know the type of Alice, contradicting the fact that we figured out the type of each. So the only leaving the first and the second cases out, and that only leaves the third case left. This is when Alice is a knight and says no. Since she's a knight and said no, then that means Bob must be a knave in order for Alice's statement to be true. In order to be true. And C is the answer that we should pick. I told you to keep the fact that I was able to figure out the type of each in mind, as that was very helpful in trying to deduct what the type of Alice and the statement she said. And now, moving on to the final and the most difficult problem, I think. Problem 4. Oh yeah, I got it. There's also a Burmese version too. Yeah, you can also read that, but I can't really seem to read it because it's kind of blurry. Sorry for all my Burmese people there. Father, will you give me my chocolate? Okay, your chocolate is in the 500th box. If you're good at counting and if you're patient, you can have your chocolate. Here is the counting rule. Count from the first box to the 5th box. Then continue backwards, starting from the 4th box to the 1st box. Then forward from 2 to the 5th box as shown below. This is the index. This is the index of the box. This is the index of the box. This is the index of like the last box we opened. Yeah, this is just the last box we opened. For example, the 6 will correspond to the 4th box. So is 12. Then 3. Then 11, 7, and 3 will correspond. 7 and 11, the 7th and 11th place will correspond to the 3rd box. The 10th and the 8th will correspond to the 2nd. Basically, any number that is in the same column as one of these top numbers, that's the box. And the question is asking us, on the 500th box, what box is the 500 box that we count? What box is the 500 box that we count? Is it the first, second, third, fourth, or fifth? Pause the video if you want to solve this problem. There's a genius solution to this, but I won't tell you but I won't tell you until now. Any number that is below these, that's the first. Yeah, for example, any number below this 3, that all these numbers will correspond to the third box. All of the numbers that are below this 4, that is all the numbers that are in the same column as 4, they will correspond to the fourth box. The numbers that correspond to the numbers that are in the same column as 5 here, they will correspond to the fifth box. And the numbers that are in the same column as 1 will correspond to the first box. We don't have much data here, so we'll complete the so we'll add more to the table using the counting value earlier. Wait. Still not enough data. We'll add more. Let's add more using the same counting rule stated before. Okay, this is enough. What do you see about this pattern? Okay, what if we separate when? What if we separate these? So the total numbers for each of these is the total numbers is 13 for every of these rows. What else do you see that is very important? Okay, you don't see it? How about now? Really? You still don't see it? Well, if you did see it, well, the last number of these rows is always a multiple of 13. It makes sense because we're adding. It makes sense because we're adding 13 numbers per row. So what I'm thinking is that we repeat this a certain amount of times such that the last number that is a multiple of 13 is less than 500. So let's say 13n. We want the minimum value. That is okay, bruh. There we go. So 13n was less than 500. I'm thinking if we repeat this process 100 times and then we'll multiple times such that 500 is in our current list. So we must have a maximum range where 500 is in. Is less than 500. Let's assume that n was equal to, say, 30. That's a good number to start. Let's see if that inequality is true. 13 times 30. We know 13 times 3 is 39. So 390 is less than 500. Okay, no. Sorry. There shouldn't be a greater than, there should be less than, as we'll find the range, as we'll find the minimum range where this exceeds 500, so that we can count back and find where so if so 30 won't work. How about 90? 13 times 90. Quick maths. That's 1170. Way greater than 500. We won't do that. Okay, how about a smaller number near to 30, like 39? Quick maths. We get 507. That is perfect. It is greater than 500, and the difference is small enough that we can calculate manually. Well, since this is a multiple of 13, since 507 is a multiple of 13, and that every number of the same column corresponds to the box, corresponds to the original box ID. It doesn't matter if we take 39, 26, 13. They're just multiples of 13. So if we go back 7 indexes, we'll get the index of the box. So 507, that becomes 506, 505, 504, 503, 502. Using the same counting rule, 507, then the last becomes 506, 505, 504, 503. Okay, maybe I should make these numbers a little one. 504, 505, 506, 507, 502, 501, and 500, using the same counting rule. Said 500 is in the fourth column, the same column as 4. As I stated, and from what I've stated before, any number of the same column as the very first number, that's the of the box numbers. All these numbers will be equivalent to that box number. So 500. So the 500 box is the fourth box, and that's the answer for the 500 box. We didn't work hard. We worked smartly. Why count manually when you can find a pattern and then use that pattern to work it out quicker and get your rewards quicker? I hope you enjoyed this episode. If you have any alternate solutions for all the problems mentioned here, please put that down in the comments below. See you in the next video. Bye bye. Oh, yeah, I think in the next video we'll probably mention about why like the sum of the numbers 1 to n is like n by n plus 1 divided by 2. Yeah.